All right. Hi, guys. So 4.4, this is the last topic in the section. Remember, you do have to do the reading in Cornell notes, and there's the 10 questions that go with it. On Kognity for this week, we're in week 3 of quarantine confinement. Please make sure that you get the readings done. Again, doing the Cornell notes, that'll help you with the questions, and it'll also help you with the big question and final exam that we're kind of going to be doing at the end after your project that you submit. You'll have all of next week to work on your project, so don't worry about that. But this is after that, then it's going to be review of all of topic 4, and then you have kind of an exam that you'll be able to use your notes with. So if you don't have good notes, it's going to be a little bit difficult. So you need to make sure that you really get them done. Also, if we do happen to come back to school and we see each other again, which will be fantastic because I miss your beautiful faces. I really do. It's very boring. You guys lighten my day. So I do miss you. And I hope you guys are doing okay. All right. But if we do come back, then I'm actually going to be grading your notes. So you need to make sure that you have those. Remember, they have to be handwritten. If you don't, I'm not going to be grading them. So it's kind of a gamble that you'll have to take whether to or not to. Okay. All right. So significant ideas. This is for 4.4. This is based on water pollution. You've kind of already gone through a topic on ingenuity through pollution, but this kind of brings everything together with the IB perspective. So water pollution, both groundwater and surface water, is a major global problem that affects where the effects of which influence human and or other biological systems. So not only does water pollution affect biological systems and fisheries and aquaculture that we talked about before, but also human health. Oops. Sorry. And these are the big questions you can look at later on. Okay. So anthropogenic, which is created by humans, or natural. So when we look at these river systems, these aren't made up. These pictures that you're seeing are literally what is happening. So this is a picture, I think, from Bangladesh. The one on the left was showing solid domestic waste. People use that water still for drinking and bathing, and they do all the same. We have what's called the red tide, which you actually will see a lot in Florida as well, where the ocean systems and stuff start to turn red. It's caused by an algae bloom. The red is actually a high increase of phosphorus intake that ends up being implemented in there, which means that it's usually very toxic. It's very toxic to shellfish and other marine species. So it's kind of like you've suffocated them, and they end up attaching themselves to these different phosphates and nitrates, and that's what creates the red tide that's you're seeing there. Nutrient pollution. So a form of water pollution refers to contamination by excessive inputs of nutrients. It is a primary case of eutrophication of surface waters in which excess nutrients, usually nitrogen and phosphorus, are going to be present. So phosphorus, we have kind of seen that mostly shows up in livestock and crops. We also see urban and population-related sources, and then, of course, just natural sources. Phosphorus, and that's the Gulf of Mexico. We also, in nitrogen in the Gulf of Mexico, are going to see things that come from crops, some livestock, urban areas, atmospheric deposition, so things coming from rainfall, and then 4% natural. For phosphorus, this is the Chesapeake Bay, which is up in like the Virginia area and Maryland area. You're kind of seeing a lot of the more livestock. You have a lot of municipal waste, urban population, and stormwater. So you're kind of seeing the difference of what we're looking at. Then some crops, and then natural. Where in the Chesapeake, again, you're seeing a lot of urbanization, livestock, crops, and then you're also seeing a lot of deposition. So this comes from manufacturing plants or things along those lines. So based on population densities and what you're looking at for those, that's going to change kind of where the pollutions are coming from. Pollution sources in this diagram are primarily freshwater. How do they become marine sources? So pretty much what we're looking at here, think about it for a second. Where does marine sources come from? If we are looking at primarily freshwater, so here's our freshwater system. We're looking at stormwater fall off. We're looking at different areas. We're looking at livestock runoff, commercials, with stuff that gets into the atmosphere, industry. That's all going into either a lake system or a river system. So what is that causing, and where did that come from? Is that, well, all rivers lead to the ocean, but we also have different marine sources that can be an issue that can attack the freshwater. So you have things like commercial boating and commercial boating that kind of goes into waterways, kind of like what you see here in Savannah. We have such a large port system that can also be a way for that to be introduced. What other sources not included in the diagram is specific to marine ecosystems? And again, you want to think about aquaculture. When we have different things in aquaculture and we breed non-GMO fish and those go out and breed with wild fish, that can cause contamination. Eutrophication with other species causing those algae blooms can also create those different types of pollutions. There's a lot of different finite things that can go into that. We have, of course, what's called point source versus non-point source. So point source solution means that I can see it. There it is. That's the pollutant. Here it is. I can figure out what's causing the pollution. Hold on. I have a train coming. It's a small train. All right. So you have non-point solution that goes right there. And then, of course, you have the that was a point solution. The non-point solution will be what's on the right. You can see that there's stuff going to be drained off and that it's coming from the water systems and the waterways, and it's going to go out into the ocean system and the freshwater system, but you can't tell me where the pollution is coming from. I can say it's coming from the street, but that's not a point. Point solution is the actual place that you can blame it on. A non-point solution, point source is, you can't really determine one exact location where the pollution comes from. Direct, which is dumping dye and other toxins into the waterways as disposal method from textile industries. Specifically, this one is from Bangladesh. So the water system is actually purple, and that's because that particular facility in that area, not really the homes that you see here, it's more coming from the industry that's coming down here that goes through a water system that pumps out into the freshwater, kind of washes away the dyes that they're using, and that ends up contaminating the water. You have indirect, which is on the right, which is excess nitrates that enter the waterways from agriculture, fertilizers, algae blooms. That causes eutrophication. So if you've ever seen this before, which I'm sure you have at some point, where it's kind of that scummy green top, that means there's excess nutrients that are in that water system that are coming from the runoff of usually fertilizers that came from someplace else. The Great Pacific Garbage Patch. I think some of you have actually done a case study on the Great Pacific Garbage Patch when we first started. So if we're looking at the Great Pacific Garbage Patch, it's what it's called. In the Pacific Ocean, there is a giant island that is garbage. There it is. It floats around. It gets caught up in those water currents that we've seen, the Great Barrier Belt, the Great Conveyor Belt of the ocean currents that are producing. And those things actually get caught in the same water system, and that produces it kind of being all confined in the same area. Okay. Plastics in the ocean. So this is kind of showing you what the garbage trash kind of looks like. And give me 1 second. Hey. Okay, sorry. All right. So Great Pacific Garbage Patch, and we also have plastics in the ocean. This kind of shows you the idea that it gets off into the system. It kind of gets caught up in the currents and then ends up just kind of floating and rotating around. That's kind of where it comes from. Okay, so organic, human and animal waste are examples of organic waste entering the water system. This on the left here that you're seeing is how So India is very, very poor, right? Based on the caste system, we have a very high level of people at the top that are wealthy, and then the majority of the country is extremely poor, really, really poor. Think about what poor is to us and then drop that about 50 more times. That is, so most places don't have public water systems. So this is actually a public bathroom for a small village in India, where you go across this little board, you go inside, and then your waste and fecal matter and urine kind of all drop into your water system. This is the same water system to which they will bathe and they will drink out of. Yeah, so this would be what we call the kind of a slum. That would be in India, which is the majority of people that do live in India live in the slums. We also have inorganic, so oil spill cleanup this is in Sundarbans in 2015, which is an example of inorganic waste. Again, this is another location in India as well. You're going to see a lot of bad river systems in both India and China. And why do you think that is? Very good. Yes, that is correct. Increased populations. The greatest amount of populations are found in India and China. There's no way that they can control those populations using those water systems because they need the water. And it's definitely a way for us to see we need to start thinking about when our populations are going to have a massive increase, what we're going to need to do. This here is the Yukon, Alaska, which is the Black River. It's mixing with the Porcupine River. So here's the Black River, obviously, and that's the Porcupine River, and they're kind of merging together. We're seeing, of course, that there's an increased amount. When it's called black sediment, that means that you have a lot of sediment in the river, which means it's a lot of, could be fertilizers and nutrients. It could just be a lot of silt and a lot of turned up and upwelled dirt and nutrients. And so where do you think some of those might be coming from? Right? So farming, dredging, and fishing practices, maybe recreational. It could also be habitat degradation, so runoff from like maybe a clearing of lands and deforestation that can end up producing those solids into the riverways. So somewhere downstream, that's what's occurring, and that gets washed away, and that's why you see the difference between the two different rivers that are kind of coming together. For Alaska, it's happening because of deforestation. Decreased in dissolved oxygen levels. So fish need oxygen in order to survive. Dissolved oxygen is the amount of oxygen that is dissolved into the water, which is good. If you have low dissolved oxygen, then that's not good for your fish. If you have high dissolved oxygen, then you're great. So as the dissolved oxygen starts to decrease, then you're going to end up having more fish maybe not being able to reproduce as much. You have a lot more death rates in fish populations. You also lose biodiversity. Ecological impacts increase because of toxins, effects of reproductive system, increase in metabolic rates, and then of course migration. So this is showing you right here that this is the temperature of the water. So we can see that there is a huge factory pumping out a bunch of heat, and then this is the cool down phase, or this is actually a waterway that's underneath it, so you can't see the heat coming out. And then it comes out of that waterway and it just releases that heat into outer areas. As that heat is being released, that increases the level of evaporation, and so as you increase that level of evaporation, you're having less oxygen present. So this is what is causing less oxygen, dissolved oxygen, in the water systems that can result and all those different problems with fish and other biodiversity life and phytoplankton as well. How might the water of the hyacinth, which is called the Icoronia crassipes, invading this lake affect productivity in the lake? So this is the water hyacinth. So here it is, chilling on the lake surface, blocking everything up. So how is that going to affect this lake's function? So if you have it blocking, you're reducing the amount of sunlight that's being absorbed into that system. You're also reducing the amount of dissolved oxygen that would be available, which causes what we call eutrophication because of the increased pollution and sediments. You've created more habitat. So there's more habitat on the surface for this particular lake, which means you have new species moving in, which can be invasive and causing a lot of issues and a lot of problems. So, possible effects. Here are the things that can happen. It's kind of a list that's down for each of you. Eutrophication, which is blocking off the dissolved oxygen and the light source and taking away those primary producers like the phytoplankton in order to be produced for food, creating less dissolved oxygen. You also have the loss of biodiversity of species and habitat. So the water hyacinth are actually going to block off the habitat available. Increase in disease and pathogens, exposures to toxins and radiations that they were never before. Bioaccumulation and biomagnification in food webs. So if you have a fish that has a disease and then a primary consumer comes and eats that fish, and then a secondary consumer comes and eats that other larger fish, and you create that chain of toxins moving up and up into the chain, and that's going to biomagnify because you can accumulate more and more and more, which creates a greater toxin in your larger tertiary or secondary species. Disruption of the breeding grounds and nesting sites, so where they used to go and breed, it was probably blocked off now and they can't do that anymore. Damage to coral reefs, of course. Coral reefs need that sunlight and that energy in order to rejuvenate and renew. And then, of course, damage to organisms, ingesting plastics, cotton debris, and things along those lines. We also have pH, nitrates and ammonia, dissolved oxygen, conductivity, which may indicate dissolved polluted water or presence of heavy metals, turbidity, and fecal coliform tests. So all of these are tests. So these are how we actually test the quality of an aquatic system. This includes the pH, the temperature, the turbidity, which is the suspended solid. So it's like how clear or how muddy is a water system, how many metals are in there. So if you can take a conductivity tester and test water and it lights up, that means there's some metal that is actually in that water. Nitrates and phosphates, of course. So these are kind of the ideas that you look at for each of those. And these are the types of tests that you would do. So if your IA includes anything that involves the water system or the quality of the water in the water system, these are the tests that you would be taking. When we talk about biodegradation in organic materials and oxygen, we're talking about things that can actually cause like decomposition, which can lead to other toxic gases. So there are different microorganisms that can grow by using various compounds found in manure, both in the presence and in the absence of oxygen. So the microorganisms can also be classified according to the compounds that they consume. So you have your organic and inorganic molecules, and then they biodegrade, and then under that they actually can create new substances. And so these are kind of the new substances that they end up creating, which is CO2, H2O, other metabolical byproducts such as methane, methanol, and ethanol. So when you have organic things that are not being broken down, when you break those things down, just like in chemistry, anything that can be broken down, you create a new substance, but the new substance that is being created can be very harmful. So when you talk about methane and methanol and ethanol, they're very harmful if you're talking about them being in an aquatic open system. That's going to now be a toxic or a toxin to other life that's living there when you talk about these different microorganisms that end up breaking down in the system. Okay, so then we're going to talk about BOD. So BOD is biochemical oxygen demand. It is a measure of the amount of dissolved oxygen required to break down the organic material in a given volume of water through aerobic biological activity. BOD is used to indirectly measure the amount of organic matter within a sample. So it increases inorganics, provides a food source for decomposers. So the more organic compounds that you have, now you have more, it's more of a food source for decomposers, so there's more decomposition that's going to occur. Decomposers must respire to eat, So they need to have that oxygen. Respiration consumes then the dissolved oxygen that's around. So you have a lot of organic material. The decomposers eat that organic material, but now when they're eating that organic material, now they're going to be using dissolved oxygen that's in that water in order to complete that process. So the demand for oxygen increases proportionally to the number of decomposers. So that are generally is going to be bacteria. So when we start to see what the levels of oxygen are doing, we're going to look at and say, oh, well, now I know how many organics compounds are actually going to be present into the how much biological chemical oxygen demand is there. So for instance, if we have sewage discharge, so again, when we're talking about these organics, that means we're talking about biologically live pollutants that are going to be broken down, things like fertilizers and sewage and manure, bodily functions, those kind of things. So if in this case we have sewage discharge, this is kind of our discharge that ends up creating. Our BOD, again, our biochemical oxygen demand was very, very low, but then this is our dissolved oxygen. Our dissolved oxygen was very, very low, but then starts to increase very greatly. And then we have our BOD, which is our biochemical oxygen demand, which ends up decreasing more and more and more because, well, if we don't have any dissolved oxygen and that's in there for the demand that we have, that means that there's a higher level of respiration that's consuming that dissolved oxygen that ends up creating it. So this is where the consumption ended up occurring. Once that consumption was done, then it kind of goes, the BOD goes down, the dissolved oxygen goes up. But this is the rate where we saw a lot of dissolved oxygen in demand, and then our BOD, because of that sewage discharge that was kind of being broken down in that particular area. The amount of dissolved oxygen requires for decomposers to aerobically break down organisms' matter in a given volume of water. And then, of course, if enough oxygen is present, aerobic decomposition by microorganisms will continue until all the waste is consumed, which is good. But then it can also be bad because once that is broken down in decomposition, that's when you're producing those methane and other pollutants and toxins. Unpolluted natural waters have a BOD level of about 5 milligrams per liter or less. And so if we look at other polluted areas, you're going to see that BOD actually start to increase, which means that would be something that would be bad. Okay, indicator species. So it's organisms that show something about their environment by their abundance or their scarcity. So if I see a lot of them, or if I see less of them, that's indicating that there's something going on based on what there should be. The species are sensitive to changes in an environment factor, so are often an early indicator of pollution in the ecosystems. So because they're so sensitive, if something happens to them, then we know that there's something wrong with the environment. Freshwater indicators are going to be things like frogs, toads, mayflies, larvae, water louse, and sludge worms. So these kind of tell you when something wrong is going on based on their population because of their sensitivity. So the mayfly, you can see in a stream, pollution level is low. Dragonfly would be in a low. Freshwater shrimp are slight pollution levels. We have hog louse, which is in medium pollution levels. And then you have a lot of tubifex, which is worms that will be in high pollution levels that actually start to show up. So remember, it's about the minimization or the abundance. So you might not just see them all die off, but you might see some species that are abundant and the other ones are not, based on the pollution level. And then, of course, if you're in extreme, well, nothing lives. Biotic indices, which we call the Trent Biotic Index, is an indirect measure of pollution by determining the relative abundance of organisms present and classifying them by their tolerance level, which is their diversity or their abundance based on a scale of 1 to 10. So used in conjunction with BOD as invertebrates are sensitive to decrease in oxygen concentrations. It's often used to compare two ecosystems or 2 point sources of pollutants, or comparing it using the biodiversity, which means they would be using the Simpson's Diversity Index. Measures the effects of pollutants on biodiversity, not the pollutant itself. So just the effects and it's measuring the tolerance and the abundance of the species that's there, but it's not really measuring an actual pollution that you have. So this is the biotic index. And then it kind of, again, we have the pollution level in the animal species of our our indicator species. And this is our biotic index. So this is based on, okay, this is how many species I have versus how much the individual species are there and how much they can tolerate. So how much that these can withstand within that given area. And then that rating will tell you, oh, if I have a 7.26 to a 10, I am very poor, up to a 0.0 to a 3.75, then I'm very excellent. So the lower the biotic index, the better the water quality. And this kind of shows you the degrees of the pollution. So this is the biotic index. You don't need to know this formula, but you might need to use this formula for something in the future. So biotic index shows you the summation of your total number of individuals of a species times the tolerance rating of that species. So whichever rating that they would end up having as far as a tolerance goes. And then you would divide that all by the total numbers that you collected as a whole. And then you would end up getting what your biotic index would end up being. So this is site 1. So site 1 shows you that we had the nymph fly, which had 8. And then the freshwater shrimp, there were 2. And then there were no tube effects worms. And then for the total tolerance levels that you have, so it's a 9, a 5, and a 1. You're kind of, remember, just basing it on this 10 scale for what they have as far as tolerance goes. So if you look back at that, it's kind of just a generalization of what their scale is. So then you're going to work out your equation. So if I do summation of Ni times Ii, again, which is your number of individuals times your tolerance rating, this one gets an 82. And then for the total N, which was 10 species in total, ended up being collected. So you got, 72, then 10, and then your total N after calculation was 10. That ends up being this summation of 72 divided by your N as a total that you end up having will give you a biotic index of an 8.2. So again, if we look at an 8.2, that is reasonably good. Where are we at? 8.2, very poor. Hold on a second. Why is it? 8.2 water quality is reasonably good. Why is this backwards? Yeah, this is backwards. This scaling is backwards on the biotic index. Because 10 should be good because you have more index than variety. So don't look at that scale. All right. Okay, so anyways, we'll look at this. So 8.2 is good. For this side, for site 2, after the collection and the calculations, they collected total species of 20. They worked out that their summation was 92 altogether. So they did their Ni times A for each of those and then just added these together. And then you divide it by 20 and they got a 4.6, which means there is some pollution there. So the lower the number, the greater that the pollution rate. I don't know why that chart is backwards. The chart is definitely backwards. So these rates should be flipped for each of those. All right, eutrophication. It occurs in lakes, estuaries, coastal waters. It receives inputs of nutrients. It's usually going to be, remember, nitrates and phosphates. That results in extra growth of plants and phytoplankton. So when you have eutrophication, that means you have a lot of things that are growing, but it doesn't mean that all those things are growing, but it doesn't mean anything. I'm sorry, hold on. So many things going on at once. All right. It doesn't mean that things are growing. It just means that it does mean that things are growing. It does mean that you have an overabundance of things when you have excess nutrients. When you have a lot of nutrients, things want to take those nutrients in, and then it goes into a boom, which can be bad because if you have so many things on the surface, you're blocking out the light. That reduces the process. Freshwater or oceans, again, sorry. Freshwater oceans have the red tide. And then, of course, we have natural or anthropogenic, influenced mostly through using fertilizers containing nitrates and detergents containing phosphates and sewage. So sewage that we use that gets run off in our houses, that ends up being usually phosphates, and then that comes from your detergent. And then we also have things that come from just agriculture and fertilizers that get washed out. That ends up being um, your fertilizers. That also ends up kind of adding more manure and stuff that increases that decomposition, which increases that biotic material. Hold on. No. Jeez. Okay. All right. I'm sorry. I'm gonna try to get through this as fast as you can. All right. So nutrients was into river or a lake. This kind of shows you what the eutrophication looks like with an increased phosphates. High levels of nitrates and phosphates lead to increased algal and plant growth. Algal blooms block sunlight from penetrating deeper into the lake. Lack of sunlight causes and die of decomposers population, means you have a growing more significantly, increases decomposition and consumer population, which leads to decreased dissolved oxygen, which leads to low levels of oxygen, resulting in everything being dead. Okay, this is what we can say, that it can result in what we call dead zones, where you can go to a place and there's nothing living. There's no life on the coast. There's nothing growing around the beds of the lake. Everything pretty much is dead because it's kind of run off that whole system. Eutrophication occurs in water bodies when too many nutrients are introduced. Too many nutrients are introduced. This is often near farm fields where farmers apply excess nutrients to the soil in order to promote growth of their crops. So you have fertilizers, you have leaching, which is actually when fertilizers and sludge kind of leach into the ground and then go out through the groundwater. You have runoff from the surface. Fish, of course, are suffocating. Excess algae blocks the sunlight, and you got little dead fishies. That's a little dead fishy. Threatens the survival of fish and other forms of aquatic life. This is what eutrophication causes. Deterioration of water quality and limits access to safe drinking water. What is it? What is it? Come here. Come here. Come here. What is wrong with you? Oh my goodness. Okay. You want to help? Okay. All right. He's going to help. Deterioration of water quality and limits access to safe drinking water, poisoning and impact of human health, and then endangers fishing, degradation of recreational opportunities, pretty much just causes devastation on the whole front. Okay. Dead zones in the Baltic Sea. So this is kind of, the Baltic has areas where there's dead zones that are there. Hold on.